When we combine aqueous iron 3+ with isocyanate, which consists of a sulfur, a carbon, and a nitrogen, and is a negatively charged ion, we get a reaction that combines the iron cation with the isocyanate anion to form a complex that has a 2+ charge. This reaction can be symbolized as we have here: aqueous iron 3+ with aqueous isocyanate forms aqueous iron isocyanate complex. However, there's no reason why this reaction can only go in the direction that we have written it. This iron isocyanate complex could fall apart to form thiocyanate and iron, and so this reaction could occur in the backwards direction as well, which we can symbolize with an arrow going in the backwards direction. Reactions that go in both directions are called equilibrium reactions. So they go in the forward direction and the backward direction. When a reaction comes to equilibrium, there will be a constant concentration of products and a constant concentration of reactants. But this reaction continues to occur in the forward direction and the reverse direction. The difference is that every time I make a product, I also have a product fall apart and become reactants. Let's watch an animation of this reaction to see what we mean. So in this animation, these green balls that are surrounded by water molecules are the iron 3+ aqueous. They're hydrated by water molecules. The yellow, black, and blue is the isocyanate. So there's an isocyanate anion, again surrounded by waters because it's an aqueous solution. And then the isocyanate connected to the green ball, to the iron, is the iron isocyanate product. So as we watch this video, let's look to see when the isocyanate forms and when it falls apart. So here's one forming, and when that forms, one falls apart. So again, we can see that one falls apart, one forms. And so when this occurs, we have a constant number of complexes, free irons, and free isocyanates in solution at all time, because every time we make an isocyanate complex, we lose one to form isocyanate and iron in solution, replacing the iron and the isocyanate that we used up to form the complex. So you can see that the reactions are constantly occurring in both directions, but they occur at the same rate so as to keep the concentrations of reactants and the concentrations of products constant. This is what we mean when we say that equilibrium is dynamic. That is, it is always in process. The reactions are always in process. It's not static. It doesn't stop. But the reactions continue to happen, but they happen in such a way that the forward rate is equal to the reverse rate, and that requires that the concentrations of reactants and the concentrations of products are constant. And so we can know that we're in equilibrium in a particular reaction because our reactant and our product concentrations will be constant, and so anything that we do to measure those concentrations will have a steady value. They will have a constant value. Notice that I could have symbolized this reaction just as easily as iron isothiocyanate aqueous falls apart to form iron 3 plus aqueous plus thiocyanate minus aqueous, with the reverse arrow depicting the formation of the iron isocyanate complex. These two ways of showing the reaction are equally valid. Now you might ask then, what's the reactant and what's the product? Because in this depiction, the reactants, as I have them written, are the iron and the isocyanate, and the product is the complex. In this way of depicting the reaction, the reactant is the complex, and the products are the separated ions. So it's very important to note that when we're talking about equilibrium reactions, we need to always symbolize the reaction that we're talking about so that everybody is on the same page in terms of what we call reactants and what we call products. By convention, whatever is on the left-hand side is the reactant, and whatever is on the right-hand side are the products.